Hello everyone, today is day 10, the fundamental theorem of calculus. I'm going to use FTC for short. This is kind of why we do calculus. So what is the purpose of antiderivatives? So we've been working with derivatives the last couple of days. We did antiderivatives before that. We're going to go back to antiderivatives again. So why do we do these antiderivatives or integrals? So I'm going to go over a problem that we did earlier. A car going 50 feet per second brakes to a stop in 5 seconds, and we're going to assume constant deceleration. This is key because this means that it's linear. That's important to us. I'm going to draw this scenario out like I did, I think, last week. So this is a picture I drew before. Velocity on the y-axis, time on the x-axis, and we're trying to find the total distance traveled until the car stopped from braking, and we used geometry and the antiderivative, and what we did, we found all this area that I'm doing in red. My area, using geometry, is a triangle. So it's 1/2 times base times height. So A equals 1/2. The base is 5 seconds. The height is 50 feet per second. And I multiply it all out, and my area, this red area, is equal to 125 feet, and this was my distance it took for this car to brake, and that was using geometry. So now I'm going to talk about using the antiderivative, and one way to use the antiderivative is figure out, well, what do I have? Well, because it's linear, acceleration should just change in v over change in t. I get it's negative 50 over 5, so my acceleration is negative 10 feet per second squared. That helps me figure out, maybe, that for this line right here, the equation of this line should be, instead of y, I'm going to use v equals, its slope is negative 10, instead of x, I'm going to use t, and the y-intercept is plus 50. This is the equation of that diagonal line. I'm going to use these ideas of acceleration and maybe later this line to talk about how I can use antiderivative or the integral to figure out the information that I want. So I went ahead and did the antiderivative exactly the way, I can spell. The antiderivative exactly the way that I did last time, like a week ago, where my acceleration is negative 10. I took its antiderivative, found its velocity. Because my initial value for the velocity is 50, that's my c value. And look, I get this equation, v equals negative 10t plus 50. Wow, that looks familiar. This is the equation of the line on the graph above. That's exactly the same. And then when I want to find its displacement or its distance, I did d equals the antiderivative of my velocity, and at the initial time, my distance is 0, so I get d equals negative 5t squared plus 50t. Again, we did this last week, so this is not new to you. So I go ahead and plug in 5 for t, because that's how long it took to brake, was 5 seconds, and I plug it in here. I get my distance at 5 seconds is equal to 125 feet, which is exactly the same distance I had when I did it by using geometry. So how does this relate? Well, I'm going to make everything smaller so we can see everything. And here's the idea. Using the antiderivative found me this area. It found me exactly this area. So what could I have done differently? I could have done that my distance or my area was the antiderivative of my negative 10t plus 50 dt using my equation of that line. But I'm going to plug numbers in the bottom and top part of the antiderivative. I'm going to plug in 0 and 5 because this is the initial time, and this is my ending time. And this distance is equal to the area under the curve. And that's what we're going to use an antiderivative for. It's finding the area under the curve of a given equation using calculus, not using geometry. I can use geometry for this one because it is a triangle, but not everything's going to be geometric in shape. So why do we do these integrals or antiderivatives? And it's find the area under the curve, between the curve, the function, and the x-axis. So I'm talking about this area. I'm going to color it in. So when I talk about area under the curve and in between and over the x-axis, I'm talking about this area that I grade in. Here's the thing. This function is a weird-looking function. Can't use geometry. That is no geometric shape that I can take as derivative. So I'm going to use calculus, and we're going to use something called the fundamental theorem of calculus, also known as the FTC. What we're going to do is we're going to talk about how we can how I'm going to do my antiderivative like I've been doing and figure out what is my area. So I have to know, for a function, I have to know what the antiderivative is. So capital F is the antiderivative of the function f. So I'm taking this antiderivative, except now I'm plugging in numbers. All I'm doing is plugging in numbers a and b. And all I have to do is, after I take the antiderivative, I take those a and b, and I plug them in to my antiderivative, and the number on top is called the upper, and the number on the bottom is called the lower limit. These are my limits. So this is my upper, this is my lower, and whenever I do this, I plug in these numbers, it's always the upper limit minus the lower. This is called the definite integral, because when I do the antiderivative here, I do not need a plus c. Those were called indefinite integrals, or general antiderivatives. These are specific. These are not general. I have a definite integral, and the integral is the area under the curve between points A and B, or this area is equal to the integral or antiderivative between points A and B on the x-axis of my function dx. This is what we're going to be working on today. Now, everything, just like we talked about velocity and acceleration, everything has direction. Area above the x-axis is positive area, and area below the x-axis is called negative area. We will deal with things with negative area. So today we're going to be working again with antiderivatives, but now we're going to be plugging numbers into our definite antiderivative and do the upper limit minus the lower limit. We'll do some examples now. So for this example, I have the function x squared, and I'm trying to find the integral between 1 and 4, x equals 1 and 4 of x squared, or this graded area on this picture between x squared and the x-axis. So obviously I cannot use geometry. That's not a triangle. It's close, but it's not a triangle. It's not a trapezoid. It's not any geometrical figure because you have one side that is curved. So I have to take its antiderivative. So the antiderivative of x squared is 1/3 x to the third, and then I have the upper and lower limits I'm going to plug in. I draw this vertical line and I put a 4 and a 1. That means I'm plugging in the upper and the lower limit values into my antiderivative, or in this case, 1/3, 4 to the third, minus 1/3, 1 to the third. Again, this is my upper minus my lower. I plug this in, I get 64/3 minus 1/3, 63/3, which I get to be 21. So the integral of from 1 to 4 of x squared dx is exactly equal to 21. That means this area here in gray is exactly equal to 21, which to me is mystifying. It's exactly the same area as a 3 by 7 rectangle. This base right here is equal to 3. So if I drew a rectangle that had a height 7, it would be exactly the same area that I shaded in gray. How does something curvy turn out to be exactly of an area of 21? I'm going to show you how I could do this on the calculator. There is a special key. We're not going to use it too often, but I just want to show you how your calculator works. Okay, I went to my calculator, and underneath the y equals, I typed in x squared. I changed the window. I decided I want the negative 10 to 10 window for the x and y. I decided negative 5 to 5 for the x was enough. And then obviously I needed bigger than 10 for the y max. So I did negative 5 to 20 because I don't really need to see anything below the x-axis. And I'm going to hit graph. And here's a picture of that graph. Looks very similar to what I did before. And now, if you go to calculate, we've done this many times in math classes. Second trace, which is calculate. We've done mins, we've done maxes, we've done intersections, and look at number 7. And move down to number 7. It says take the integral or antiderivative of this function. I choose number 7. It asks for the lower limit, and then it will ask for the upper limit. Well, obviously the lower limit for this example was, I'm going to just type in 1. Don't move the cursor, just type in 1. Hit enter. It asks for the upper limit, and the upper limit for this example was 4. I'm going to hit 4. When I hit enter, watch what it does. It's going to do it quickly because mine's on my computer. It has a high processing unit. Look, it did it from 1 through 4. It shaded between the curve and the x-axis, and it gave me on the bottom right here that the integral from 1 through 4 was exactly 21. Like I said, it's unbelievable that something curvy could have exactly area of 21. Okay, so we're going to try some examples here. We're going to use both geometry and definite integrals. I'm going to do the FTC part first. So it will, using this function here, everything's graphed over here. Part A is in green, part B is in red. The antiderivative of 4 to 10 of 1/2 x minus 2 dx. Well, the antiderivative of this is x becomes x squared, and this would be 1/4 x squared minus 2x, and then I'm going to plug in 4 and 10. So I'm going to plug in these numbers. I get equals 1/4 10 squared minus 2 times 10 minus, so this is the upper, and now I have to do 1/4 of 4 squared minus 2 times 4, and that is the lower. If I continue on, I get this to be 25 minus 20 minus 4 minus 8, which turns out to be 5 minus a negative 4. And I get that area of that green to be exactly 9 units. Okay? That is doing the antiderivative. So doing the calculus part, I get 9. Let's do it using geometry. Well, that area is a triangle, is 1/2 base times height, which is 1/2. The base here is 6. My height here is 3. And guess what? With this area, I get exactly 9 again. I better get the same, whether I use calculus, using my definite integrals, or using a geometry formula when I can. Triangle I can. So I went ahead and did this one because right now, based on what I have is, well, it's the same antiderivative or integral that I did before, except I have different limits. Instead of from 4 to 10, I have from -2 to 2. So I went ahead and plugged in my upper limit of 2, minus plugging my lower limit of -4. I did all the arithmetic work, and I got this area is -8. Why is it negative? Because that area is below the x-axis. Well, how about using geometry? What color should I use? I'll use orange. Well, by geometry, this shape is a trapezoid. Area equals 1/2 the height times the sum of the bases. Well, right here is the height. Okay, sorry about the glitch. Right here I have the height, and the height for this is 4. So I get A equals 1/2 times 4. And this base, the short little side here is -1. And this other side here is -3. So I get A equals 1/2 times 4 times -4. And I get exactly the same area of -8. I better. It's the same. It better be the same because it's the same shape. Well, let's just talk about definite integrals in general when I have letters A and B and C and D instead of actual values for x like 1 and 4 or 2 and -2 and so on and so forth. So this is asking for the area between x equals A and x equals B of this function. So it's basically looking at this area right here. That area is equal to 0.8. The next one, see, it says between A and C. I could just split that up as A to B of the function, and then the area from B to C of that function. I can split it up into 2 parts by adding them together, and I get, well, this area from A to B, which we already did, was 0.8, and from B to C, that area is right here, and that is -2.6. Wow, that's terrible. Come on, grab the eraser. -2.6 because it's below the x-axis. So that is equal to -1.8. That is the area from A to C. When I want to do A to D, well, it is just A to B plus B to C plus from C to D. Well, from A to B is a positive 0.8, it's above, plus from B to C is a -2.6 because it's below, plus a 1.5 from C to D because that's above, and I get this total area is equal to -0.3. So the total area from A to D is actually negative below. And finally, the last one, well, I can just split it up from B to C plus from C to D, and I get -2.6. I am having problems in my head with that idea. 2.6 plus the area of 1.5, so this total area is negative 1.1. Okay, the last page. So for number 3, before I even am going to take these definite integrals, I'm going to break up each little part of this graph into its little pieces of area. So all the ones in red are below the x-axis, and we have triangles and rectangles, so we have areas of like negative 0.5 and negative 1. And then the green are the positives, and we have areas of 0.5 and 1. Okay, as you can see, I did this problem while I was paused. And all I'm doing is adding up all the little areas of this figure to make up the whole definite integral in the part A from 0 through 4. I have all these values here in blue, and they add up to negative 3. From 4 to 6 is all here in green, and that adds up to 1.5. And then I did from 2 to 6, and I did all this area and all this area, and they all canceled out. They're exactly the same size. One's positive, one's negative, so the area, the total integral is equal to 0. And then finally at the end, from 0 through 6, I did all through 0 through 4 to begin with, which was part A. And then I did from 4 to 6, which was part B, and I got my result as negative 1.5. So we're going to do some problems again, where we're going to take the definite integral of these functions, and my limits are, I have an upper and lower limit, and it's very nice this time. I made my lower limit 0 for both of them. I'm going to love plugging in 0. For B, I'm probably going to have to rewrite this guy as the antiderivative of x to the 1/2 dx. I don't like taking the antiderivative of the square root of x. I have to rewrite it. So I'm going to do this first one, and I get obviously 1/3 x cubed plus 2x squared plus 3x. I'm plugging in my upper and lower limits of 3 and 0. I'm going to pause the camera. So I went ahead and did most of this problem while I was paused. As you see, I took the antiderivative of the function. I got 1/3 x cubed plus 2x squared plus 3x. My upper and lower limits are 3 and 0. I love plugging in 0. It is so nice to plug in 0, especially into these polynomials, because then this whole thing is just equal to 0. So nice. I plug in 3 as the upper, and I got 9 plus 18 plus 9. So the definite integral from 0 to 3 of this function turns out to be 36. So let me take this antiderivative of x to the 1/2. Well, it's going to be x to the 3/2. And let's see, reciprocal of that is going to be 2/3 x to the 3/2. And my upper and lower are 4 and 0. So I get 2/3 of 4 to the 3/2 minus 2/3 of 0 to the 3/2. Love plugging in that 0. So I plugged in 4 and 0 as my upper and lower. As you can see, upper minus lower every single time. 4 to the 3/2 is just 8. Half is the square root of 4, which is 2. Third is 8. So I have 2/3 of 8, which is 16 over 3. So this definite integral of this function is going to be 16 over 3. So I want to find the exact area between the x-axis and the graph y equals x squared minus 8x plus 7. I need to know the x-intercepts. I have to know where they intersect. So I'm trying to find this area inside of here. So I set this equal to 0. I have to factor this. Not a lot of choices for 7. X minus 1, x minus 7. We'll give them a negative in the middle. So I have 1 and 7 as the x-intercepts of this. So this is 1 and this is 7. So I'm going to do the integral from 1 through 7 of x squared minus 8x plus 7 dx, because what am I trying to find? I'm trying to find this area. Exactly. Ooh, it looks like it's below. My area is probably going to be negative. So 1/3 x cubed minus 4x squared plus 7x from 1 through 7. This is my antiderivative. Now I'm going to plug in 1 and 7. As you can see, I plug in 7 and 1 as my upper, my lower, and I get 243 over 3 minus 196 plus 49 is the upper, minus 1/3 minus 4 plus 7 as my lower, equals negative 98 over 3 minus 10 over 3, which is negative 108 over 3. I get negative 36, and I better get negative because it is below the x-axis. So this area here is equal to negative 36, or from 1 through 7 of x squared minus 8x plus 7 dx is equal to negative 36. And this is the area between the x-axis and the function or the parabola.